Hello everyone, welcome to my talk. My name is Qiao. I will present a new framework called DINoMe to present an interpretable non-interference measurement and demonstrate its application to processor designs. Data privacy is a critical challenge not only for software developers but also for hardware designers. To achieve functionality with optimized performance, hardware designers tend to do data-dependent optimization, which may expose unexpected information linkage in hardware modules. And even worse, some information linkage is already discovered by the talented hardware designers with suggested solutions. Many of us still underestimate the risk due to the lack of automatic tools that can generate quantitative and interpretable measure to help us understand the linkage. We still need a lot of manual efforts from domain experts to diagnose the root cause of a linkage, prioritize the issue based on the severity of a linkage, and propose a patch to fix the issue. Our work would like to explore a more automatic approach to measure how serious this linkage is, and also give some readable hint about how the linkage happens. Clearly, the most challenging part of our work is due to the complexity of the system. First, to implement a framework to capture or compare examples showing the information linkage. Scaling to multi-cycle executions in a real processor is a problem if we just naively using simple execution. Second, to generate a readable measurement, the combination from different sources of interference in a system may scare the users and make the final measurements less useful. And in this talk, we will focusing on the later part about how to simplify the measurement to explain the leakage. The first problem we want to solve when generating an interpretable and quantitative measurement is how to make our evaluation focus on just undesired information flow for a system, which includes multiple sources of interference. CPU hardware channels surely can review the secret contents if your software intends to review that part, because your software execution is fully absorbed by the hardware modules. There would be lots of false positives if we did not rule out the software-defined leakage due to desired software logic. To isolate the linkage due to different reasons, we can incrementally add some declassification rules to evaluate the additional linkage while ruling out known and unconcerned secret linkage. Another question we would like to answer is how to make our measurement more interpretable. One naive idea is to generate secret input pairs that lead to different observable values, and then mark our lines of code snippet executing those examples. However, when it comes to the software-hardware defined boundary, we need to highlight both software and hardware code from many functions and modules. In practice, finding an expert who can read both software and hardware code is difficult. To solve this issue, we propose an approach to explain the interference via an interpretable model, not relying on how the code is written. To support the quantitative and interpretable measurement, we implement a framework called DINoMe to evaluate software-hardware combined information linkage and test its effectiveness using some small software workload running in an open-source RISC-V processor. In the first step, instead of using symbolic execution, we just use a logical translation function provided by a synthesis tool called IOSIS to translate a Verilog specification to some SMT2 formula, which represents the one-cycle state transition logic from a fully symbolic hardware state to the next states, and also generate an initialization logic, which treat the software as inputs to the memory models to initialize the memory for the future execution. And then we can incrementally compose a logical formula for multi-cycle execution by stitching the initial logic with the translation logic for multiple cycles. Then, and during stitching step, we can take sharp SAT preserving optimization to simplify the post condition while still keeping the desired solutions. We then can later we can apply our desired declassification technique to rule out the software-defined information linkage and focusing on unexpected information flow. And after that, we can generate a formula representing the interference and use model counting to count the solution and use sampler to generate representative input and output pairs. And finally, we can calculate the information metric to quantify the information linkage and train a machine learning model to interpret the information linkage from the software and hardware. To translate systems post-condition to a formula representing information linkage, we need to model the input and outputs for the post-condition using a general security model. Here we consider a victim software which carrying a secret inputs running above a real processor implementation. However, the processor implementation may include some unexpected hardware channels that could be utilized by attacker via some attacker-controlled inputs and by observing attacker-observable outputs. Then we can prove that the system holds the non-interference property if the attacker's observable does not differ between any pair of secret values with the same attacker-controlled inputs. To measure linkage based on non-interference property, DINoMe uses a quantitative measurement proposed in a recent work. The basic idea is to use the J-card distance metric to measure how easy an attacker can distinguish between two secret set S and S prime using attacker-controlled and attacker-observable variable as the attacker's view. Then, by tweaking the secret set size, the J-card distance between the attacker's view will describe the linkage pattern in a quantitative way. And however, that measurement does not include a declassification to rule out some some expected information linkage. In order to incorporate declassification into that measure, we first define the declassification information using delta as a function of CINS. And that declassified information could be available to any users, including attacker. Then we can combine this delta information into our post condition to represent the procedure, and then the new post condition will represent all possible attacker-controlled, secret, and observable, and the declassified information that are available in this procedure's execution. Then we can define a new set D, which sub S, to represent all possible attacker-controlled and declassified information when secret comes from a secret set S. And then if we want to rule out the information linkage from the delta, then we can add a constraint saying the attacker-controlled and the declassified information should belongs to the intersection of D sub S and D sub S prime, which indicates that this declassified information should be available to both secret set S and secret set S prime. To give you some motivation about why we need this declassification and how we use the declassification in the quantitative measure, here we give 3 simple and naive examples. The first procedure allows attacker to review the 5th bit about a secret while an implicit workflow. The second procedure allows the attacker to review the first 5 bits of the secret while explicit flow. The third procedure allows an attacker to review the first 4 bits and the 6th bit about a secret. And using the original J-card measurement, it's very easy to understand that the procedure 1 needs fewer information than procedure 2 and 3. However, if we are provided with a context information about system saying that this system has to link or need to link the first 4 bits about secret due to its functionality, then we should take this classification information into account when we are measuring the information linkage. In that sense, procedure 1, 2, and 3 should all just link one additional bit. To achieve interpretability, we trained an interpretable classifier to generate interference rules. Specifically, the classifier can tell us whether a secret pair S and S prime will cause interference when the attacker chooses attacker-controlled variable C. The critical part in this training is to generate good samples for input pairs, and to get secret pairs with attacker-controlled variable leads to interference. We need to define interference sets, including all possible C, I, S, and S prime combinations. Specifically, when the attacker chooses attacker-controlled variable C, the execution should be feasible only for a secret come from set S, but it's never possible for the execution with a secret come from S prime. To rule out interference caused by the declassified information, the set also should assume that the S and S prime secret share the same declassified information value. And then we can generate solutions in bit vector format using SAD solvers. To support easy-to-understand relationship between variables, we then convert those solutions into different formats using code context information. In the first step, we reconstruct the variable to their original types based on their definition in codes. The second type feature we added is a symmetric feature. That's based on the fact that for each interference rule, we can trivially exchange the position for S and S prime to construct a new interference rules. Thus, for each secret variable, we added a symmetric difference between S and S prime. To represent simple but useful rules, we also use a local linear model to find some useful linear combinations between different variables to allow the decision tree to use a decision node with multiple variables. During the training stage, DINoMe uses gradient boot tree to generate decision tree in symbols, which use many small trees together to make a decision. Then DINoMe can extract rules along the path from a root to each leaf. The rule will have an associated precision and recall to indicate the quality of the rules, and the DINoMe will also trim and rank those rules based on the precision and recall, and use them to explain the linkage. One information linkage we evaluated using the open source RISC-V BOOM core is the linkage due to Spectre attack. So here we will represent some interpretable rules extracted from our framework to explain the information linkage in this Spectre attack. So here we have a list of rules with associated precision and recall. And in the first rule, we have 3 predicates. The first predicate indicates that the attacker-controlled variable offset should be larger than the array size, which means we should try to access all the boundary memory. And the second predicate tells us that the branch predictor should have has a very special states for this entry 0. And the third predicate indicates that a secret should have some difference at some bits. And then we can see from this table we have several similar rules with the rule 1, and those rules together can represent that only when the branch predictor is carefully set to a specific state, the secret bit 0 to 3 will be linked when the offset is out of the array's boundary. In conclusion, our work first proposed a framework and implemented the prototype to measure information linkage by ruling out some defined linkage using declassification rule and explain the course of interference using interpretable model. Thank you very much for your attention, and I hope you enjoyed the talk.